To begin this project, I began creating the design using Onshape, a free browser-based CAD software. I was introduced to Onshape from my robotics team. However, you've probably seen it as a sponsor for many YouTube videos. Unfortunately, we're not sponsored by Onshape, but it is a really great software. Another big benefit of Onshape is that it's free and has unlimited public storage. I designed big mounting plates to laser cut, as well as several 3D printed parts. My brother and I were joined by another guy from our robotics team who's an absolute Onshape wizard, and he designed the entire launching mechanism and mounting bracket featuring a clip-in magazine, which is totally unnecessary but totally awesome, which kind of represents the kind of guy he is. I mean, just look at these things. For this project, we used an ESP32 rover module with its GPIO extension board, battery casings, two ROHS step motors, and their drivers, bearings, plus a breadboard, two DC motors for the flywheels, and a ton of wires. As parts begin printing and assembly starts, let's talk about the software side of things. As I mentioned before, we are using an ESP32 for our brains. Our ESP32 is basically the same as an Arduino, with the added bonus that it has Bluetooth and Wi-Fi capabilities. With few lines of code, we can set up Bluetooth communication with my brother's Mac Mini. This thing is a beast. The turret is going to use computer vision AI to track a Darth Vader helmet. Andrew's Mac Mini will run the AI model and send commands to the turret's ESP32 via Bluetooth to tell it how it should move. We trained our own computer vision model for this project. First, we took about 150 pictures of ourselves with the mask in various places and poses throughout the room. Then, we used roboflow, a website completely focused on computer vision. While you do have to pay for some of the advanced features and training on their servers, the basic features that we utilized were completely free. After we took our pictures and uploaded them to roboflow, we had to manually annotate all 150 images by drawing a bounding box around the Vader mask. Then, we just head on over to the Versions tab and download our dataset to our computer. The dataset contains 3 folders, both with resized images, and their respective annotation coordinates. The dataset also contains a .yaml file that defines the file paths and each of the objects, in our case, just Vader. Next comes the magic part of this process. To train our AI model, we use the ultralytics Python libraries. Ultralytics is kind of like roboflow, but for training YOLO datasets. You can sign up for a free plan or a paid plan to do various things, but as it turns out, you don't even need to do that. Following their documentation, you can pip install the ultralytics libraries for free and do anything yourself. By browsing their resources, we figured out how to use their libraries and now have the ability to train our own model. Now, even the Mac Mini would struggle to train an AI model, so to fix that problem, we decided to use Google's servers. Yes, Google's servers. I did not know this until someone showed it to me, but Google actually has a feature called Google Colab, which allows people to run Python scripts in a Jupyter Notebook format on Google servers completely for free. So, making sure we set the runtime type to Python 3 on a T4 GPU, we could train our models super fast. After running each snippet in our Jupyter Notebook, we had our AI model, which we could then run on the Mac Mini. To run our new AI model, we used the CV2 Python libraries. Using the CV2 libraries, we wrote our script to take the camera input and analyze it with our AI model. We then sent commands over Bluetooth based on the results. For instance, if the bounding box was to the left of the camera, we rotate the turret counterclockwise. If the bounding box is above the camera, we rotate the pitch axis upwards. And if the bounding box is in the middle of the image, kapow! 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 With the Mac Mini, the tracking was super smooth. At this point, enough of the turret was assembled so that we could begin testing using Andrew's phone as a camera. However, even though our code was working, our turret didn't seem to have enough strength to move itself consistently, as you can see in this clip. Just trying. From our analysis of the problem, we figured out a couple of ways to make it work. Our first idea was bigger stepper motors, but bigger stepper motors need more power, new mounting brackets, new driver boards, and we were running low on time to do all of that. The second idea was to lower the teeth width on the gears. They were pretty chunky, and the lower teeth width should reduce friction. This idea was better, but we had a better one. Our bearing underneath with marbles inside. We use big marbles, that's what the turret rests on, and then we use these smaller marbles as spacers. Our problem was friction in between the lower gear and the upper mounting plate. While we had a spacer, it wasn't really enough. All of the weight of the turret was pressing down on the spacer, making it extremely difficult to turn, especially for our little stepper motors. Plus, we hadn't even put on the shooting mechanism, which would add a ton more weight. Since we didn't have a turntable bearing, we made our own with some 3D prints and marbles. Unfortunately, our spacer made it so that our old gears didn't actually mesh, so we had to print some new ones. I had the great idea to turn the old gears into spinning tops by hot gluing a couple of little 3D printed hemispheres onto the bottom. Unfortunately, these proved to be a little too fun. Robotics. Things were shaping up and the final product was in sight. We worked to attach the launcher to the turret and had a couple small hiccups. We had issues with the flywheel not revving up to the expected speeds, even with excess of battery power. We only figured out that our capacitor wasn't rated to handle currents that high until after it had melted. So this is an example of a design error. I printed this here, but as you can see, there's no way to actually put it in. And the crucial axle piece failed its 3D print 1 day before show day, which was super stressful. Luckily, we were able to pull it off, and here are the results. Also, we 3D printed these little plastic darts with hot glue tips to weight the ends. Don't worry, they are so light that they hurt almost as much as a Nerf gun, even at their high speeds. Turret online.
Alright, good job, robot. Yeah, so it's like aiming at him up and down. Alright, so if you take off the mask, then does it aim at Daniel then? So it's trained to only recognize the Darth Vader mask. Alright, now put the mask down and see if it aims at you.
So, if we were to make an AI turret 2.0, I think there would be a couple small changes we would make. The first change would be to decrease the teeth width of the gears. It would reduce friction, thus making the stepper motors more effective. Next, we would adjust the mount for the launcher. The flywheel motors made the mechanism a bit too front heavy, and that made the stepper motor have trouble moving the shooter up. But if we center the weight on the axle, it will make things easier on the stepper. Bigger stepper motors would be nice, although I think more refinement on the design would make it unnecessary. Also, if you haven't noticed, our turret uses a ton of batteries. 10 AA batteries and one 9-volt battery to be precise. It would be awesome to add a power distribution board and use one of those rechargeable Milwaukee power drill batteries to power the turret. Finally, I think it needs an outer facade. I think it would be sick to make it look like a Star Wars turbo laser. Let me know what you think. Thanks for watching.